assay standard curve looking a bit too curvy? You can improve the linearity of a Bradford assay by taking the ratio of absorption at 595 or 590 over 450. This is going to improve your linearity and your sensitivity. Why? It has to do with how the assay works. It uses Comasi Brilliant Blue dye, so that dye that you use to stain proteins in your gel, we use it here as well. And the way that it works is that this dye has multiple forms, and so it has this form that is red colored that is going to predominate under acidic conditions. And these conditions are acidic under a Bradford assay. And so you have this free red dye, but then when it binds to a protein, it gets stabilized in its blue form. And in that blue form, now we see a shift in the absorption of the light. So we go from absorbing maximally around 450 to absorbing maximally around 590. And so we typically measure the absorption at 595 or 590, somewhere around there, in order to figure out the concentration of our protein, because the dye bound to the protein is blue, but the free-floating dye is red. But there is a kind of range of absorption. So there's a spectrum, and the peaks for the free form of the dye and the peaks for the protein bound form of the dye overlap. So there is signal from the free dye at the wavelength of 590 or 595, somewhere between 590 and 600, depending on your spec and things. In that range, you also see absorption from the free dye. And that absorption is going to go down as the dye gets used up. So this means that your background is actually going to decrease as you have more protein. But typically when you're making a standard curve, you're assuming that the background is constant. The background is not constant, though, it's decreasing. And so what this means is that you're going to actually underestimate how much protein you have at those higher concentrations, because you're kind of like assuming that the baseline is staying here, but really it's going down. Also, what's going down is the amount of free dye. And the binding of the dye to the protein is reversible. It's an equilibrium reaction. As the dye is getting used up, the concentration of dye is going down, which makes it so that binding is less favorable. So you have these multiple things going against you at these higher concentrations. You can take this into account by taking the ratio of the 595, or again the 590. So in the original paper, they used the 590 because that's what their spec reader was able to do. But you can use anywhere basically in that region, between like 590 and 600. And then you divide that by the 450, where the free dye is. That takes into account the fact that the amount of free dye is decreasing over time as the amount of the bound dye increases. And so by taking this ratio, you're able to get a more linear curve. You're able to increase your sensitivity. You make a curve that, because you're kind of measuring these two different values, but they're connected, what happens is you get a steeper curve, and it's going to then have better sensitivity, and you have a larger range in the linear region. So taking that ratio is going to help improve your Bradford assay, but you still are kind of limited in your range. And so we actually found a lot better luck with the BCA assay we tried yesterday, and because it's based on the backbone as opposed to side chains, it has less protein to protein variability, but it does take longer than a Bradford assay. And more on other types of protein quantification methods in yesterday's post.